You've read number 20? Yeah. So, the reason I asked you to read this, I'm going to do something like it, because the next lesson, it kind of has a similar idea to what's happening in number 20. So, sometimes, with these distributions, you'd like to make an interval. You want to find 2 points, so that most of the data is between those 2 points. So I'll give you an example, like with the heights we were doing. So we have our heights, and we'll say that the average height is 160, and we'll say the standard deviation is 10 centimeters. And I would like to find two numbers, here and here, the same distance from 160, and I want this area, for example, to represent, let's say, 95%. So in other words, I want to know, like, boundaries. Yeah, boundaries, so that most people's height are between these two numbers. Will everybody's height be between these two numbers? No. 95% will be. Yeah. So I'm looking for, in this case, a number. What will I call it? Don't call it X or Z. Delta. Yeah. So we're looking for, let's say, mu minus delta and mu plus delta, and I want it to be 95%. Okay. So the first thing I need to do is look at this as a Z transform. What would be the mean here? It'd be 0. And here, I call it, I don't know, minus small delta, minus small delta, minus small delta, and positive small delta. Sorry, this is small delta, this is big delta. I don't know how good you are with your Greek letters. This one? Alpha, beta, gamma, delta. Alpha, beta, gamma, delta. Yeah, if you didn't know that, you can write those letters down. Anyways. Oh, what happened to you? Bus late or student late? I think there's a big difference. Okay. So, if I want this to be 95%, what do I need to do with my table book? You see, our table book, we normally look for this number and it gives us the area. But this time I want to go backwards. I want the number that makes an area of 95%. But how much would this area be all to the left of delta? Not 100%, because 100% would be everything. 97.5%. So we actually have to go backwards. We have to go to the table book, but we want to go backwards. We want to look at the answer. We want to try and find 0.975, because you figured out, Victor, that this is a 5% here and this is a 2.5% and this is a 2.5%. So if I want this number here, I need to look up 97.5. So can you look at your table book and try and find the answer 975 and see what Z that was? No, just the number, yeah. So you have 0.975. So this is 1.96. Yeah. Okay, can I go down?
Why inverse?
Well, we're literally going backwards. Instead of looking for the area, this time we have the area and we're going.
We have the percent.
Yeah. Okay, can I go down? Yeah. You have to look for 0.975. There it is there. And you want to read it backwards. It'll be 1.96 will make this area. Yeah? So you're reading it backwards. You have the answer and you want the number.
How did you know 0.975?
Because my question was I want to make 95%. So the area to the left of here is 97.5. Because if that's 95, that tail must be 2.5, and that tail must be 2.5.
Why we cannot use 95%?
What do you mean, in the tables?
Yes.
Well, if I want 95% from the center, the tables only tells me everything to the left. So I would need to look up 97.5. If I looked up 95, it wouldn't give me what I want at the start, which is 95 in the middle. Okay, we're good now with this? Right, so if I draw my bell curve again, we've worked out that if I want 95%, I need to go minus 1.96 to the left and 1.96 to the right. Remember our formula is Z equals, Z equals X minus mu over sigma. Yeah. So we want to go backwards here. So if I rearrange this, I'll get X equals mu plus Z sigma. And we know what the Z is here. What is it? What's the Z here in this one? 1.96. There are two values of Z, aren't there? So it's actually mu plus or minus 1.96 sigma. And this is kind of the key step I wanted to get here. At the beginning of the question, I said the mu was 160 and the sigma was 10. So 95% of people's height will be between these two numbers.
1.96.
Times 10.
Oh.
Yeah. So this here, this is called a 95% interval. So, in fact, because 95% is such a common question in these problems, it's actually like 95% common. It's such a common question that a lot of students, and I think this is perfectly fine, a lot of students just remember this result, that if you want to make a 95% interval, you can use this formula, the average plus or minus 1.96 standard deviation. This will make a 95% interval. And that's so common that it's perfectly normal to remember this. That's fine. But I wanted to show you how I did it, just in case the exam asks for, 99% or 90%. So this is the important result here, the formula. Okay, so if you want to just take note of this example. Yeah? Okay, can I continue? Yeah. So now we can have a look at the next page now that we have that idea. Don't know if it will be No, I don't think it has too much, but maybe if I open up the graphing program, Excel. Okay, so one common problem in statistics is finding the average of something. So for example, you might want to know what is the average height of students. So the way you would do that is you would get 20, 50, 100 students and you would measure their height. So we imagine that I got 20 students and I measured their average height. And then maybe Malik, he gets 30 students, he measures their average height. And then somebody else, maybe they get 10 students and they measure their average height. Will these results be the same? No, they won't be the same, because each time when you sample different groups of people, each time you sample you get different people, and there'll be slight differences each time. But what about if, for example, that's actually a letter. If I sample 1,000 people, and then somebody else, they sample 1,000 people as well, we'll say. What can we say about the differences here? What do you think? Will it be a big difference, a small difference, the same? It'll be very tiny, yeah. And if you make the n bigger, it'll be a smaller difference between the two. Whereas if you have something silly like 10 people and 10 people, there'll be a bigger difference between the two. So in your mind, you're picturing the problem like this. We're trying to find the true mean, but we can't, because each time we sample, we get different people, which will make a different average. So the problem is the sample produces different means. So let's imagine we have 10 people doing this research. So first I get one average, Malik gets another average, Victor gets another average, etc. Let's say there's 13 people here. We have something called the standard error. It's like the standard deviation, but it's not, I should tell you what it's not first, it's not the standard deviation of the height. Okay, it's not that. It is the standard deviation of the average of the height. So in other words, if you look at how different these estimates are, the standard error is what we call the standard deviation between the different averages. And that's not the same thing as the standard deviation of the heights. That's a different thing. And I'll try and show you that in Excel. I don't know if you need to write anything here, but in 1 minute I'll give an example in Excel. Okay, so let's have a look in Excel. So here are 10 numbers, and I know that I know what the true average is. The true average of these 10 numbers, it should be 0.5. That's not important, but I know what the true average is. So I don't know, let's say these 10 numbers represent heights of a plant. So the height of some kind of, I don't know, small tree, whatever. Let me just put in a row above. So let's say this is Malik's data. He went out to the forest and he measured the height of 10 of these plants, and he got an average, mean average height. And let's make it 2 decimal places as well, since it's height. And so there you go. There's his 10 heights, and he got an average height of 0.43. Let's insert a column here. So this is his mean average. have a look at his data and roughly, very roughly, tell me what you think the standard deviation of his data is. Like a rough guess, if you look at the data, how much is it changing by? No rough guesses? Go on, yeah? What do you think, Tony? I think so. I think something like 0.225, something like this. So we'll calculate it. So you can see 0.26. And again, let me put that to 2 decimal places. Right, so then next person, Victor, he does the same thing. He goes out, he finds 10 different plants, he measures those heights, he gets the average as well. So here is his. And you see this time he gets 0.557. But notice how his standard deviation is still about the same. And then next person, you go out and she gets 0.43 and the standard deviation is also about the same. So one good thing you notice is that even though they have different samples, at least their standard deviation is nearly the same, but their averages are quite different. He got 0.43, he got 0.51, she got 0.43, so again it's closer to his. So let's go across and make some more here. 0.52, okay, we'll do, can I squeeze in one more? Okay, I think that's good. Of course, each time I move it, it changes since it's random. Alright, so here is everybody's attempt at trying to find the true average. None of these answers is right. They're all people's guess at what they think the true average is. But the standard error, that is the standard deviation of all these guesses. So let me calculate that. The function is stdev dot p. So before I hit the answer, if you look at all those averages, what would you say the standard error is? Just a rough guess. What does it look like? 0.3? Oh no, too big. 0.15? 0.15? Maybe a little smaller. Let's see what we get. Not too bad, Tony. 0.11. Can you see how that's different to the standard deviation? It's not the same thing. It's how much the guesses are changing by. Yeah. Now, there's one small thing though about standard error. It's not. Well, no, I don't. It's not quite as straightforward as 0.11. Well, it is, but I think I'll stop talking now because I'll make it confusing. So I'll give you the formula here. There is a way that you can put limits on your guess. So you want to know, okay, the height. I know I won't get the true value. I know I'm only getting an estimate from my sample. So I would like to have some kind of limits. So just like my example I did, the true average, I'll write it like this, true average, it will be smaller than my average which I got from the data, which I called H, but for my formula I'll just call it X. This one here is from my data. This one here is the true one. Here's an X. This is from the data. Minus something and plus something. If you want 95%, you won't be surprised that the formula has a 1.96 in it and a plus 1.96 here. And what goes here is the standard error. But you can't really calculate the standard error unless you have many people doing the experiment. So we put something else instead, which is actually almost equal to the standard error as well. And it's the standard deviation. Now before you go crazy, I know I just said it's not the same thing as the standard error, the standard deviation. So we put in one extra thing to adjust it. We divide by the square root of the sample. So if the n gets very, very big, what happens to this piece? If the n is very big, it's very small, which means you have a very accurate guess at the true average because you shrunk it down. If the n is small, what happens to it? It gets big, so you have a big interval for your prediction of what the true average is. You've seen this before. Have you ever seen in a survey, it would say something like 20% of people like, now let's make it more like 90% of people like or love DIFC, for example. And then underneath it would have plus or minus, 5%. Have you ever seen that in a survey? Or maybe you've never noticed it. Never noticed, yeah. Next time you see a survey, down the bottom it will say this plus or minus part. That plus or minus part comes from this. It's like the error. It puts boundaries on the prediction of the true value. So of course we know it's not exactly 90%. It could be as small as 85%, or it could be as big as 95%. So this here is, it's like an error. It's how much you could be off by in your prediction of the true average from your sample. Yeah, okay, we get the idea. So this is called, this here is called a confidence interval. And in fact, 95% confidence interval.
Now, excuse me?
Mm-hmm.
What do you calculate like standard error? Like when you just add one interval, yes.
You can't calculate the standard error. This is the problem. But you could calculate the standard deviation. And when you divide by square root n, it equals the standard error. So in other words, Malik, you can say the standard error is roughly the standard deviation divided by square root n. Yeah? Can you see how standard error is like a type of standard deviation? Yeah. Now, as Malik was asking me, how can you calculate the standard error? You can't really calculate it unless you have many people doing the same thing you're doing, because the standard error is the difference between each person's guess of the true average. But you can calculate this from your data. A lot of books write it actually like this, because the S, to be technical about it, when we write sigma, it means the true standard deviation, and when we write S, it means the standard deviation from our sample. Now, if you look at my data, you can see that the standard deviation is kind of the same for most people, except for this weird one here. So the standard deviation from our sample is probably accurate. So for this level, IFY level maths, we don't worry about the difference between the two. But at university level, when you do statistics, you will. So there is a difference between this and this. This is actually the true value. This is the value we estimate from our sample. But as you can see, the differences are quite small, so we can just take them to be the same. And the formula is not exactly this either, but for this level, it's accurate enough. Okay. Now, if I go back to my data here. How big is my n? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So, Malik wants to estimate his standard error. So the formula is standard deviation divided by square root of 10. So you see he gets 0.08 as what he thinks the standard error is. Now it's not going to be exactly 0.08, but you can see it was actually 0.07. So you can see the formula is pretty good at estimating the standard error. So let's do that for everybody. So you see, it's not a perfect thing, okay? But the important thing is we have some attempt at trying to limit what we think the true value is, and that's the key thing. Now, it's not clear in the syllabus if they want you to use other things than 95%. You know why I have 1.96, don't you? It's like from what I did earlier. The formula book, yes, if you have the formula book and if you go to page 8, you see page 8? Can you see that the 95% confidence interval formula is there for you? The second formula. So I think they only want 95% in the exam because this is the only one in the formula book, but they haven't actually said in the syllabus if this is true. But just looking at the formula book, it looks like it's only 95%. Okay. Right, so I want you to try some of these for a few minutes. You could start at like number 3, I think, if you want. I mean, you can do 1 and 2. Just 1 and 2 takes a little bit of time. Number 3 is short enough for class. So you could try 3, 4, 5, and 6, for example. Okay. Can I close this?